Okay, today we're going to talk about momentum. So momentum is a vector quantity of mass and motion. Should make sense if you see the equation there. It's talking about m and v. It's similar to kinetic energy, but a vector instead of a scalar. So it's kinetic energy we talked about last time was the energy of a mass in motion. It's the same idea except for energy was a scalar. And so this time we need a vector. We need something with direction. It's measured in kilograms meter per second. Normally we write them like that, but with a multiplication symbol between them. So I write it like this, kilograms meter per second. And momentum it's a P and it's equal to m times v. And it's that simple. Obviously, we often will start simple and things get harder as we go in physics. It'll be the case. We'll be using this a lot. We'll be applying it to things and it gets a bit more complicated. But for now, it's pretty simple. P equals mv. Okay. So let's find the momentum of a 60 kilogram halfback moving eastward at 9 meters per second. If we use the equation, all we have to do is plug in the numbers and we get 540 kilograms meters per second. It's that simple. But remember, it's a vector, so we need a direction. So we need to attach east to it. If we're given specific directions, we should add the east or west to it. If they're not given us specific directions, we need to make sure we add positive or negative to know our direction. So 40 kilogram freshman's moving south at 2 meters per second. We got a mass of 40. We have a direction or a velocity of 2, so we get 80 kilograms meters per second. It should be a times kilograms meters per second. And this would be south. And of course, if we weren't going to use the word south, we would want to put a negative. Because if you remember our compass, just like a coordinate plane, up and to the right are positive and down and left are negative. So that means north and east are always going to be positive, and west and south are always going to be negative. Okay, I'm going to get my calculator real quick. So, impulse is the change in momentum. And we just write it as delta P. There are special letters. Sometimes you'll see impulse written as J, or you'll see it as I. I just use delta P because that's what it means, and that's the simplest way to think about it. It's equal to the change of momentum. Remember that delta is final minus initial. Delta stands for final minus initial. And so in this case, delta P is P final minus P initial. And it has a special equation. Turns out that this delta P, this P final minus P initial, this definition, it's equal to force times time as well. And we can use that to solve some problems. Let's first work with an example strictly off the definition. Delta P is defined as P final minus P initial. So let's plug in what we know. Well, P final is going to be equal to mass times V final, right? That's the definition of momentum. P equals mv. So that means P final is equal to m times V final. So that's equal to... So that's equal to 72 times 7, which is equal to... Let's look. 72 times 7, 504. And then our, P initial is equal to m times V initial, which is equal to 72 times 2. So it's equal to 104. Not 104, 144. So 144. And when you subtract them, you should get 360 kilograms meter per second. Oftentimes when we write delta P, though, we'll go ahead and just plug in the equations for PIF and PO, PF and PO, and write it like that. And then we can just plug in the numbers like this. It's a little bit easier to work with. You can also see here that we could factor out an m out of both these terms. And so sometimes it's easier to work with this equation. So we'll try this one on the next slide. Let's say a roller coaster uses an air-powered launch to speed up the 400 kilogram car from rest to 48 meters per second in 4.2 seconds. What is the force required to do this? So here's our definition for delta P, and it's equal to force times time. So again, I said we could also use this equation. Delta P is also equal to mass times Vf minus V naught. And so we can throw that in here. It's another way of writing the same thing. It's just factored this time. And then let's throw in our numbers. Our mass is 400. Our V final is 48, while our V initial is 0. So you can put in the minus 0 if you'd like to, but it's just going to come out to 0, right? Minus 0 doesn't mean anything. And so 400 times 48 is 19200. And then if we divide by 4.2, we get that F is equal to 4571 newtons. Lastly, let's try this one. 15 kilogram shopping cart experiences a force of 45 newtons for 3.8 seconds. If the cart started at 3 meters per second, what is the final velocity? Let's go ahead and use, instead of the other delta P, let's use this one. Just for fun, we're going to try all the different versions of the ways to write delta P. They all mean the same thing. They're all different ways of writing the same thing. So don't feel like I'm using a bunch of different equations. They're not equations. They're just all definitions. They're all different ways of writing it, though. So delta P equals Ft. This is the only equation that you really need to know. Delta P happens to be equal to F times T, but that's not a definition. In this case, our delta P is V times Vf minus M V naught is equal to F times T. Our mass is 15, and we're looking for the final velocity. Our mass is 15, and our initial velocity was 3. Our force is 45, and our time is 3.8. Okay, so we get 15 Vf minus 45 equals 171. And then we can go ahead and add 45 to both sides. We get 216. And if we divide by 15, we should get 14.4. That's our final answer. Overall, it's not super complicated. It's just, there's just a bunch of different ways of writing the same thing. And so I show them here. Delta P can be written in either two ways. It can be written like this, which is the thing. It's PF minus P naught, right? PF of both, because remember P is equal to M times V. And so we can write PF as M times VF and then PO as M times VO, which is just the definition of change, final minus initial. We can also take this right here and then factor the M out. And if we factor an M out of both terms, we're left with there's this minus this. And so we're left with M times VF minus V naught. Okay, so those are two different ways of writing the same thing, and they're both equal to F times T. And you should be able to use this to complete the homework, complete the assignment, and turn it in. That's all I have. Thank you.